Great. So let's get started. So, so today we're going to talk about um, uh, um, how do we think of communities in graphs, mostly based on social networks, and how do we find communities in graphs? So I'll also kind of give some history lessons a bit in this lecture, not as much as the last one. Okay, it's the end of the semester. There's a lot going on. Let's review a few things before we get into the lecture itself. Okay, great. The final report you all turned in, that's done. That's great. That's kind of the big whopper on the schedule. The other one is the end term test. That's going to be in class on Wednesday. Like the midterm test, you'll be able to bring in one sheet of paper, front and back. You can put anything you want on there. I suggest you kind of spend some time to write what you think is useful on there as a good way to kind of doing studying. It won't be open books and other stuff, but you can look at that one sheet of paper so that you give you a lot of stuff to work with. It will cover everything that was not covered on the end term, starting with the streaming section, which we did not cover. Sorry, was not covered on the midterm. So this streaming section, then dimensionality reduction, which was kind of had the most lectures in it, and then there'll be stuff on the noise section and the graph analysis. Okay, so I will tell you they'll still be roughly the same length, but this one will have 4 kind of big questions on each of those, kind of one of those on each of the topics, and then some subparts within them, right? So I will tell you that about the end term, but I think overall the overall length of it won't be kind of any longer. It'll just be spread out over 4 questions instead of 3. So that some of the questions won't be as long as they were on so the midterm. All right, so aims will be roughly similar to that. There's a practice test here where you can get some sense of there. So I haven't gotten around to kind of writing up or posting answers to that, but if there are any questions, you can ask. I might get a chance, maybe, I don't know, I have a deadline on Tuesday, so maybe on Tuesday, but if there are questions, you can post them, and I will get to those on Canvas pretty quickly. Last year I looked up, I didn't post answers, but someone else, which was okay, wrote out what they thought were the answers, posted them on Canvas, and then there was a discussion about it, right? So that's another way of kind of crowdsourcing. And if there's questions in there, I will monitor it and I can jump in if there are kind of confusion about what the right way to do something is. Okay, so also our great so Eliza finished grading 6A. It is sitting, it needs to be transferred over to Canvas. That should happen today or tomorrow. So you'll get the feedback on that soon. The graphs homework, I recommend completing it. Is it due before the end term test at 1 o'clock? Okay, so then strongly recommend completing before the end term test. I think forcing you to go through that will be really good practice for what's going to be on the test. That's why we structure them in this order. Great. Okay. The other stuff coming up is there is a poster outline and then a poster presentation, which is your final exam. Okay, the poster outline is due Thursday, December 4th. This is the last date I can actually legally have something due. It'll be through, upload to Canvas, and I will look through them and try and give them feedback. and then we will print them for you. Okay, there was a $15 fee or something for the course, and that goes towards printing the posters. So we will handle all that. So then on the poster day, which is scheduled to us by the kind of exam office, our final exam slot, you will show up by the front office in the Merrill Engineering Building, if you know where the school computing front office is. I will have all the posters there, probably around noon. I'll probably aim to be ready to go. And you can set them up. There'll be poster boards and stuff, and you'll have kind of a sheet you'll have to kind of complete while you're there, going around and seeing other people's posters and stuff. Should be pretty straightforward. A couple of people I know in the past were a little nervous about it, but then told me afterwards it was so it was actually a lot of fun. Okay, so you get to go see everyone else's poster, what they worked on all semester, and see it and talk to them, and you get to vote on the best poster. The best poster will get some extra credit, right, as voted on by your peers. And you should prepare a 5-minute overview for me to describe your poster, 3 to 5 minutes. And I will come around and need to visit all the posters. And so I need to do that within 2 hours. So I will have to move through fairly quickly. So you'll have 3 to 5 minutes prepared, and then I will ask you a few questions about your poster. And so this will be your final exam grade. But so the poster outline due December 4th is for me to give you feedback, and basically in some cases I will say approve, we can print this if you're ready, but in other cases I will say, you know, I want a little bit better structure in a certain way in the posters. I can't share online posters, their previous work from people in class, but I can bring them in, and there are some examples up here of kind of ones that were approved in the past, and you can get a sense now that you've done your reports, look at these posters and say, this has a cool idea. It should be very figure and table and chart forward, right? That should be kind of the star of the poster. The text is kind of secondary there, just a little bit of kind of connecting tissue between the main aspects, which are the figures and charts and maybe some key equations. Right. So the title and the name should be on there, and they should match what was in your report, so I can line everything up. People will be assigned to go and review your poster. All of you will be assigned someone else's poster, and so it's key that the titles match up so that they know which poster to go and find. All right. Any questions about all the stuff that's upcoming? Final exam posters. Print them in, 2 by 3 feet. You can do them horizontal or vertical is okay. I tend to like I guess I'm old school. I still watch most of my videos that are more horizontal than vertical. I think it works better with your eyes. Your eyes are kind of spread out that way, but some people, I guess all of you nowadays like the vertical video stuff, right? So maybe no. Okay, well, I like the horizontal ones. You can do 3 columns. It kind of works out kind of nice. Yeah.
Given the bigger load, would it be too much to get 2 note sheets instead of 1? I know you mentioned last week you don't want students to go through their notes and waste time.
Yeah. How about 1.5? Okay. Yeah. That'll be fine. I need to. Yeah. So. Yeah. So I'd be fine with 1.5. Yeah. Yeah. Okay. Any other questions on this? Great. So let's go through the topic for today, and if I do get through a little bit faster, I can kind of review some stuff from the second half of the semester as well. All right, and if you need, and also if you want some kind of guidance on what to do with the poster after today, there's a bunch of stuff written in the project kind kind of in what you should include in the poster, what not to do, kind of some examples here. The double check on some of the dates here. So I will probably update this, but this will give some guidance on what you should be doing to making the poster. All right. Okay. So let's talk about so detecting communities in graphs. Okay, and so this is the idea that we have a graph to model a social network. Okay, so the graph will be G kind of has defined by vertices and edges. Okay, and the vertices are going to be kind of, think of people, or it could be kind of like a business, or so in general, like an account on like a social network that's posting interesting stuff, and the edges will be measuring the interactivity. So think of like, so if one person follows another person, then you would often connect them with an edge, right? So this is a spot where the directionality typically doesn't matter as much here as opposed to in the Markov chain setting with PageRank. The directionality kind of could matter. We need to make sure things are kind of so like the ultimate network and Markov chain we model has to be ergodic for us to model the PageRank vector. Here we could model one person follows the other, but that's not is like not reciprocated. Again, the results of clustering and finding communities tend to be about the same, whether or not you include the directional information. And the directional information turns out to be kind of messier to think about. So we're just going to say someone follows the other person. But so I would like to, before we just dismiss this and think about like just modeling this as a graph, right? So then we have these vertices and these edges between people. And so you could think of modeling this as a graph. I would like to kind of pause and think about, how do we define an edge between people in this kind of an example in a graph modeling a like a social network. There are some example graphs from the early days of social networks on the web where companies were willing to give out their graphs online, or some versions of their graphs from the social networks. This is much less common now to get access to this. But these graphs kind of define an edge between the entities in the social network. And they say, okay, these people are connected to each other, and these other people are not connected to each other. But like, I think, what does the interactivity actually mean? There isn't just one way you can follow another person. Like, there is a hard relationship with this in so in Twitter or Facebook, you can actually follow them, but there's also, you might follow them but not actually interact with them. Maybe you actually, if you send them like a direct message, or you comment on their post, it shows a much stronger supportive form of interaction than just if you follow someone, or they're one of the people you have as like friends on Facebook, right? So the idea of what exactly is an edge, I think, is not so clear. And so this is kind of washed over here. For the most of this lecture, we're going to kind of ignore this sort of issue, but I want to say this is not so clear what defines an edge. So this is one reason I've kind of pushed this lecture to the end, in that I'm kind of, I think there's some potentially kind of this whole field of thinking about social networks as graphs starts with this premise that you can define an edge or not an edge between some sort of interaction. There are some cases where there's like a graph with payments between people. On one of the more recent graphs that got put out there was there was like a graph of like Venmo or something where there's a payment of some transactions in between people. Those are hard actual transactions, and those actually mean something. That makes sense as an edge. But if you're modeling this as a social network, there are so many degrees of what follows mean, and that it's kind of a little hard to understand this. Now, you could maybe have a notion of similarity between two people, which is kind of a soft edge. It could be an edge you could think of as storing, I can represent an adjacency matrix, right? Where Aij equals 1 if edge Eij is in the edge set, and 0 so 0 otherwise, right? But I could replace this with a similarity function instead that maybe went between 0 and 1. So if they had a lot of interaction, maybe I put it as a 1. They have 0 interaction, it's a 0. But if they follow them but never comment on their posts and kind of compared to other people, then maybe it's a 0.2 or so something like this. Maybe you can extend this sort of analysis to having these soft weights. Some parts might be a little bit tricky to kind of understand here, but it might go through, but this is not that common to do. So it's kind of more common to model it as a firm graph and then work directly on this. And this kind of bothers me as kind of the modeling side of it. The other thing that will be different about today's analysis is that up until now, all of our modeling of graphs has kind of turned into kind of like an eigenanalysis, right? So, where we kind of modeled the graph as a matrix in some way, did some eigen decomposition, and then you could understand it through some different matrix representation. And there are different ones we considered. There's the Laplacian representation for spectral clustering. There's the probability transition kind of representation for the kind of the random walk stuff in PageRank. And then for the graph embedding, there's kind of a variety of things in between here, right? Or we can just look at the adjacency structure. And so we're not going to do that today. We're going to talk about other kind of models that don't immediately have an eigen decomposition sort of solution to them. And that has kind of made the algorithms to work with them harder to do. Okay, I like when there's a nice simple algorithm you can run and it's straightforward and you basically get the answer that way. And it scales well as long as you know how to scale kind of the stuff in linear algebra. This stuff will not be the case. And so there's a lot more combinatorial algorithms in the space, which is kind of, they're messier to deal with. So we'll give some perspective on these things. Okay. So now okay. So the premise now, though, is we have a graph that's modeling people or businesses or accounts. We have edges between them if they interact. And we're going to kind of, this is modeling a social network. We want to find communities in the social network. So communities. This is similar to clusters. But is not the same as clusters as we defined in spectral clustering. Okay, so a community will be a subset of the vertices in a graph, and you can have a set of of communities. Okay, and these could be set C1, C2, dot, 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 CK. Okay, or should be a set notation. Each of the CJs will be a subset of the vertices, but I do not need the union over J of this is the union of CJ is not necessarily equal to the vertex set. So it may not be a complete covering of everything. I don't need to say every vertex is in some community in the graph, and it could be, and it's okay if CJ intersect C J prime not equals to the the empty set. So they can have an overlap. Okay, so let me try and give an example here. So I could have a graph that looks like this. And so again, I want the communities to have these dense structures involved in them. And okay, so now so I'm going to think of having two communities here. This could be C1. Let me add some other. Okay, so, and then I could have another community C2 is going to be this subset of the graph. This particular node V is in, let's call it VI, is in C1 intersect C2. So this node is in both of them. And these nodes are in, these nodes here are not in any communities, right? So these are in no these are not in any communities. And so I don't need to force a decomposition on the graph anymore. I just want to find these subsets of the graph which are a kind of coherent structure. Okay, so this is slightly different than the clustering formulation before. I just want to find these dense parts of the graph. Okay, and each of these, I somehow want this to be a kind of dense part of the graph. So why is this interesting to find? Why are these interesting to find in the so in the graphs? Well, so let me kind of start with kind of a history lesson. Back before Facebook, there were things like MySpace and other kind of these kind of some social networks, but they weren't as all inclusive as they are now. They weren't as an essential part of like the internet, but it was definitely true during the dot-com boom that a lot of the companies realized that they wanted to have network structure that was kind of they wanted to have kind of this critical mass so of their companies. They felt that this was kind of a new system, a new way of kind of interacting, and the first in the market would get kind of the bulk share of this new space. And if they were the first in the market, they would people would not leave them to go to something else. But there was still a small fraction of the actual community was actually online, and these people were kind of more adept at doing stuff, and they could switch between things. And so they wanted to make sure that when they were on a system, that they would be kind of invested in that system. And one way to do that would mean that they were interacting with the other people. They had a community, and this is how they were communicating. They were interacting. They had like a friendship group there. And they kind of knew they needed to get these critical mass, not just in the number, but in the kind of how connected the network was. So that wasn't a bunch of just isolated nodes, but it was these clicks inside here that were interacting and doing something on their product. And this was not just true of like the social network. So I'll tell you a story. When I was an undergraduate, I was working. So at the time I was working. So I was working in a research lab, and this was in Houston, Texas, not in kind of the Bay Area or anything. And a postdoc in the lab had just finished his PhD at Stanford, and so I found out at the time he was the chief technology officer of some company, as most people who had affiliated with Stanford Computer Science were. And my roommate in college did not have his own computer at the time he got to college. It was not everyone had actually had computers of their own in their dorm room. And there was a company where you could, when you browse the web, you could pull up, or if you have your computer on, you could pull up this app, and it would run and display ads on the bottom of your screen. And they would pay you to actually run the ads on the bottom of your screen. And so he did the math. There were a number of these companies. He figured if he bought a computer and had it on the whole time, that using half a screen, that the computer would pay for itself after like a year or two, right? So he figured he would still have better than not having a computer, and he could just run this in the background. There's something to move your mouse so it looked like you're actually browsing and doing stuff. And so I later learned out that the postdoc in the lab was the CTO of this company, right? That was putting these ads on. And there were a bunch of these companies. His company was the only one that ever actually sent money to people. Other ones got people to run ads, but then didn't actually end up sending anyone checks. Okay, so why is this interesting? Because when I talked to him about it, he said, well, yeah, we're doing these ads, but the real goal is to have a social network of people, to connect people through these ads. Different people watching the same ads and clicking on them will link them together, and they'll form a community of people. This was the vision of the company somehow. That company went out of business. So in the dot-com boom, I guess people did not want to put extra ads on their computer. There were enough ads already. But their goal for a random company like this, they knew they wanted to build a social network, a network effect of people, bring people together. This was kind of everywhere in the kind of the Bay Area at this time, that they knew they wanted to build Facebook. They just didn't know how to get there. So what is it about the network effect of these graphs? Let's talk about kind of graph theory a bit now, and kind of now try and connect this network effect with graph theory together. There were like a handful of real graphs out there. So kind of basically, each company had one graph, and there were about 5 to 10 public graphs released that people study. But so what people wanted to do is to understand what social networks stayed around and did not go out of business, right? So what are kind of lasting social networks? And so there's very little you could study. You have your one graph, and maybe you can checkpoint it at various times. And there were 5 to 10 published graphs, and these were of social networks that we kind of knew kind of what happened with. But what made a good model for a graph? We couldn't just use this handful of things we had available. We wanted to have kind of a mathematical model of what graphs are supposed to look like. Okay, and so the standard model for the graph at the time, around 2000, and and before, was called the Erdos-Renyi model. And this is where there's for with some value p, which is in 0 to 1. And so it would say that I wanted to create random graphs to study and say each edge ij equals 1 with probability p and 0 so otherwise, and these choices were so these choices were independent. Independent. Okay, and at the time, this model of graphs had been well cited by mathematicians. It's a really cool model. There's a bunch of things you can learn as you increase p as a function of the number of nodes in the graph. You have the number of nodes n and p as two parameters. You could study what happens as p changes as a function of n for very large n. At some point, you start seeing these tree structures in the graph. At some point, it becomes kind of everything is connected except for a few small things. This is about when p is roughly, yeah. So when you get a roughly, on average, n log n edges in the graph or n nodes, you see everything is connected. All of a sudden, there are these weird kind of phase transitions that happens. And the mathematics behind this is very, very beautiful and nice. And up until this period, prior to around year 2000, we didn't have any large graphs like this that we could really study. We actually were studying these social network graphs that were collected from sociology experiments. And these were collected by a person going to like high school or something and trying to physically check who interacted with who and build an actual social network by talking to people. So you'd have these social networks graphs before 2000. So real graphs before 2000 had n equals roughly 100. Okay, and there are examples of these, and people studied these. What are the graph properties of these? And maybe they look like these Erdos-Renyi graphs. We couldn't really tell. N was kind of small enough, we weren't really sure. We could find clusters and a few things, but we weren't sure what was going on. But this Erdos-Renyi graph was kind of as good of a guess of anything. Just every edge was uniform at random. But when we got to these really large graphs, these graphs had up here, these had something like n equals like 100,000 or like 1 million. Okay, so we had 100,000 to like 1 million nodes, and now we start to see stuff at some very real scales, maybe even 10,000 nodes. The smaller graphs with size 100, you could draw them, you could plot them and draw them on the screen. And there was a lot of graph drawing of how to draw graphs of roughly the size. They were close enough to planar that there weren't too many edges that were crossing. These graphs were not that way. They were much bigger and they were too many edges, and you could not draw them. If you tried to draw them, they looked if you drew them, they looked like this, Okay, and there's a technical name for this. This would be called like a hairball graph, where it's just most stuff is very densely connected, and I can't see any structure in here because there's so many edges and they're kind of going all over the place. It's hard to pull stuff out of here. I couldn't use my favorite method for clustering, where I tell you to plot it in 2D and then circle the clusters. With graphs, if you could plot it, you can kind of do this pretty well. But these graphs were so big, I couldn't plot them in 2D well enough to look and see what was going on. I needed some other way to kind of understand what was actually happening. And I could look at these for the kind of the random model, the Erdos-Redny model, but they also look like this, so I couldn't tell by just looking at this property. The first thing that struck people that was different was the degree distribution. Okay, the degree of a vertex vi is the number of edges eij in the edge set, right? So if I look at a vertex vi, right, so then the degree of vi in this example is going to be 5 because there are 5 edges coming out of here, right? 1, 2, 3, 4, 5, right? So I could look at the degree distribution and this random graph model had the degree distribution roughly uniform. It was not exactly uniform, but it was fairly uniform. All the vertices had roughly the same degree distribution. Especially as n got big, it concentrated. It was roughly kind of n times p, right? The degree in expectation, the degree of vi was equals n times p, right? So there are n other options, times p is the probability of having an edge, and this concentrated, right? But real graphs had decaying degrees. Okay, so there are some very large degree nodes, like if you think of like if you're thinking like if you're thinking of like a social network, some people like Taylor Swift or like Mr. Beast who are very popular, and then your average person on the social network does not have nearly as many kind of degrees as these people, right? So there are some very high degrees, and it kind of drops off, and you get these very high degrees and then low degrees and some very, very low degrees, right? And so this real graphs had decaying degrees, and so this was somehow different. So our first indication that these were different, and we knew that this was not the right model anymore. And so there's a scramble around 2000 of what is the right model for these graphs. We want to study them and generate a bunch of random graphs and kind of see what happens, run some simulations and stuff on them. Okay, so we need to start with kind of a model for what is a random graph. And so let me kind of get at this with a kind of a social experiment that we could run. Why do people join networks? Okay, and let me give you kind of a specific example of a question. I'm going to have an existing network okay, let's look at an example here. And now this is my existing network. I'm going to think of two people, X and Y, and they already have some edges into this graph. And this is like a kind of like you could think of this as like a group chat or some community that gets together. It could be like a church group or something. And these two people, X and Y, are thinking of joining this group and becoming part of this activity. And they have this structure. They both have the same number of edges going to this graph. In case it's 3, they have kind of 3 friends that they have inside of this structure. So I should say communities. Okay, why do people join kind of communities? This is a well-defined actual community, not just finding something on a graph. But the difference here is that X, their friends are all friends with each other. Okay, so X has what do I call this? They have kind of three friends, all so connected, and Y has three friends that are so disjoint from each other. The friends of Y don't interact with each other much inside this group. Who is more likely to join the group, X or Y? Right? And prior to kind of having a bunch of real world large graphs to study, there was a debate on which one was more likely, right? So who thinks X is more likely to join? Okay, and who thinks Y is more likely to join? Okay, great. Okay, so someone who chose X, why do you think X is more likely to join? What's the kind of theory behind the case? They're closer to their neighbors. Okay, think of like a sociologist. This is pre-2000, right? I know maybe it's hard to think pre-2000 for all of you, but like what would a sociologist's explanation for why would X be better to join? Or do you want to start with why Y is better to join? Okay, why would X not join? Okay. Okay, X is already feeling left out. Yeah. Okay, so you feel like, look, if they're not joined already, then maybe. Okay. No. Okay, yeah. Great, yeah. So X this kind of was the argument for X, in that they already have a tight knit community in here. They will join it, and they will have a group who is going to interact together. Maybe they felt left out because they were doing it without them, but maybe they had just joined this, and they were already friends, and they said, "Hey, X, you should join us too." And these three people all told Y to join. Okay, anyone have an argument for why would join?
Why would make the big closer?
Okay, because why would pull stuff together? Why would feel like I'm going to come there and pull everything together? I think the argument was more like they had disjoint support. There was one reason to join this group of friends, where Y had three somewhat independent reasons to join. Three different people for different kind of perspectives within the group were all telling Y to join. Okay, and so that was kind of this joint support versus very strongly connected support to join. Okay, and no one really knew the answer. It was too hard to run studies on this sort of thing, kind of at hand with the clipboard in these church groups and monitor them every week. It was just too hard to do. But with social networks, we could study this. We could set up a bunch of experiments where this happened and kind of look over time what actually happened. And these social networks would do this. And who was more likely to join? Well, the answer, yeah. So everyone should vote. You have to vote X or Y. Who thinks X? And who thinks Y? So Y, and some people didn't vote still. Okay, everyone didn't vote. You have to vote this time. Okay, X and Y. Okay, X is a little bit stronger. So it turns out the answer is X. Okay, this is basically X is more likely to join. Okay, and this is an example of this preferential attachment model. Okay, that you're more likely to join something or you're more likely to form a new edge if you already have kind of this strong kind of support from multiple people pulling you together. Strong networks get stronger. This rich get richer phenomenon. If there are a bunch of edge that's tightly connected, you're more likely to add more edges inside of there. Whereas if it's loosely connected, you're not as likely to add more edges inside. And this is something that has been widely observed in these kind of social networks sort of graphs. Okay, it's not exactly the same thing as this kind of who would more likely to join groups, but this preferential attachment so model is about which edges are most likely to form. And it's basically saying that so between two vertices, V1 and V2, that the probability of a new edge between V1 and V2 is somewhat proportional to the number of shared friends. Okay, a shared friend would be another node like this, where V1 and V2 have an edge here. Right, so the more shared friends, V1 and V2, the more likely to join this new edge together. So the more of these shared friends, the more likely here. Basically, the edges like to create triangles. Okay, new edges like to create these triangles in a graph. Right, so a triangle is just what you think it is. It's a set of three vertices where all pairs are connected. Right, these new edges tend to like to form triangles. This is different than this older random graph model where it was independent. It didn't matter if they had shared vertices or not. Whether an edge was joining was completely independent of all the other edges in the graph. And so you can study these graphs, these social network graphs, and they all exhibit something like this, where their new edges are more likely to form triangles than edges that would not form triangles. Okay, the more triangles are formed, the more likely it's going to add. And this leads to graphs that tend to have much more clusters and structure in them. Okay, kind of the fraction of edges that form triangles turns out to be something called like the clustering coefficient, and like how many triangles you get in a graph is proportional of edges. The larger this is, the healthier the graph in some sense. The stronger the community, the more likely is this is going to be stable, right? That people aren't going to leave because they would leave, and if they would leave here, they would leave lots of kind of common connections, right? So those graphs with lots of triangles are more stable. Okay, so graphs with lots of triangles, these are kind of more stable and lasting. Great. So we want to understand graphs that have these large triangles. And so there were a bunch of new random graph models that people use to generate and simulate graphs that somehow tried to model these statistics on preferential attachment models that you could run that somehow modeled the real graphs we did have access to. And there's not one model settled upon. There are these kind of block models where you kind of force groups in there and then you generate edges proportional to them, but they were kind of less kind of organic or hard to generate. So there are a variety of models, but they often try to follow this property. Okay. All right. So now we can talk about communities again. So these are now going to be subsets of graphs, kind of C subset of V, with kind of many kind of edges inside. Right. This is kind of what we wanted with the normalized cut, right? But they're going to be defined slightly differently. I actually want many triangles inside, but the triangles are kind of figuring out how many triangles are in a graph turns out to be kind of a little harder to calculate than edges. Edges I can read directly off of the way I describe my input graph. It's part of the input. I have the vertex set and the edge set. I can take a vertex and read off all the edges. Determining all the triangles is a little bit harder. So we're going to still use many edges as a proxy for this, but really I'd like to count the number of triangles inside the community. The more triangles, the more stable it's going to be. Yeah. Yes, right? So if I do a graph that's going to be of this model, Erdos-Renyi, this will, as I increase P, I increase the number of the edges. Okay? Real world graphs, if I look at the number of triangles in here, the number of triangles is going to be I can look at a set of 3 edges, and it's roughly P cubed is the probability that forms a triangle because they're independent. Okay, so I have there are roughly let's see, there should be n choose 3 triangles, each one times P cubed. So this means that this has roughly in expectation roughly n or in hold on, expected number of triangles is roughly n to the 3 times P to the 3. Right? There are n cubed possible triangles, and each one occurs with probability P to the power 3. Okay? On real graphs, I see a much more triangles than this because of they're generated with this preferential attachment model, where if I generate edges sequentially in the graph, one by one, then I'm more likely to add an edge that's going to form a lot of triangles. So I tend to see more triangles than I would expect from the simple random graph model. Okay. And there are a bunch of studies that show plots of these random graphs and count the number of triangles. And so graphs that are just random, right? Think of this as maybe you think of these are actually are these bots, right? The bots are just forming edges randomly, kind of somewhat randomly, where real graphs are kind of forming them in the structure. They're actually forming friendships and doing stuff together. Bots have that was old school bots. Now bots have wised up to this and trying to create realistic kind of models of networks of these things. But not that realistic. They might be closer to the Erdos-Renyi model than realism. It's not too hard to detect these networks of bots. It's just the social network companies don't want to do it because they want to inflate the number of things they have in their network. They don't care if they're bots or not. And kind of the difference between a bot and a company with an automated account or something is maybe hard to tell. So they don't. So they probably could detect and remove a bunch of bots from Twitter if they wanted to, and I think they choose not to. All right. So communities and graphs. I want to find subset that have a lot of edges. Okay, and talk about 2 ways of doing this. Okay, where they're tightly connected pieces. And let me first talk briefly about a method called betweenness. Okay, and this was, I think, a question on the practice exam about the betweenness of a graph. So the betweenness between two vertices, between V1 and V2 is going to be the fraction of the shortest paths that use edge V1, V2. Okay, so if I think of, let me kind of draw a picture here that will maybe look familiar in some ways. All right, so think of this as Salt Lake City, this as Park City, this is like Tooele. I'm probably not spelling Tooele right. Never remember, but something like that. And so there's a lot of road networks here in Salt Lake City. Everything is fairly well connected. Park City and Heber and Midway and whatever is up here in the mountain. And there's very few roads in order to go up to Park City. There are very few options to go up here. And same with like Tooele, you basically have to take I-15 or no, not 15. I do I-80 to get up to both these places, right? So there aren't a lot of options here. So now if I look at all the shortest paths, so I take all pairs of nodes, I compute all pairs of shortest paths, and I look at what fraction use which edge. Well, these edges, if I really do the shortest path, time-wise, I'm going to get on the freeway. But if I'm just looking at the shortest path in distance, I can use all these different roads in here. There are lots of ways to get between places. But if I want to get between Salt Lake City and Park City, then all the shortest paths are going to have to use this edge. They're going to have to go through here. There might be another longer route to go through here, but all the shortest paths are going to use this edge. So this edge has a high betweenness score. Okay, so this has a high between score. Okay, so the betweenness score of this edge is going to be very high, I-80, same with I-80 over here. And these edges in between are not going to have as high of a betweenness score. Okay, and so this tells us kind of something about the importance of an edge of the graph. Kind of like the PageRank vector on the importance of vertices in the graph. It's not quite the same thing. It's a different measure of the importance of nodes in the graph, or in this case, edges. I could run this. I can see the fraction of the shortest paths that uses edges in the graph. So that uses vertices in the graph and compute a between the score for vertices as well. That would give me something comparable to PageRank. This one's much harder to compute. Okay, this is more robust in some way. It kind of maybe makes more sense, but it's harder to compute than PageRank. PageRank, I have all my linear algebra tricks I can throw at it, so it becomes very fast to compute. This is kind of slow. I basically have to compute all pair shortest path, which is gonna take a while to do. Okay, so how do I get communities out of this? Once I've have this graph and I identify the edges that have the high betweenness score, how do I get the communities in this graph? Okay, so yeah. Yeah. Yeah, I'm just counting the number of hops, and it's all shortest paths. So I look at the fraction of all shortest paths. So I compute all pairs shortest paths. So from every vertex to every other vertex, and then from this one to this one, and this one to this one, I compute all pair shortest paths. So this is how it's defined. It's not. It works quite well, but it's not computationally efficient, so it hasn't become very, very useful for that reason. So but I compute all shortest paths between every pair of the graph, I look at what fraction of those shortest paths use this edge. Okay. Right. So if this is V1, this is V2, there might be actually a set of edges in between here, right? I might have some waypoints in between here, but they're all going to have high betweenness score, all the edges in here. Okay, so how would I get communities out of this? Okay, so I'm going to remove edges with high betweenness score. Okay, and then remaining so connected components, these are the are going to be the communities in the graph. All right, so afterwards, this chunk here would be a community, this would be a community, this would be a community. If there are isolated, these edges might actually have a fairly high betweenness score, even if there's not much else here. They may not have anything left to actually connect. The edges, the vertices along here that are just along this freeway might not be connected to anything. Maybe I'd say large enough kind of components above a certain size I count as communities. I don't have to have every vertex in a community, but this would be a big connected region. Park City would be a big connected region, and so and so on. So if you did this for like road networks, this would work really well for identifying kind of the areas where there are these different communities in Utah, for instance. Okay, so and I can do a similar. I could compute PageRank on the vertices, remove the high PageRank vertices, and see what's left. This might also work. But with betweenness score, this is kind of a common way to find communities in the graph. Okay, this really, what's left, things that have lots of triangles and paths in between here, they're not going to have high betweenness because there are lots of options for the shortest path to go there. Okay, let's talk about modularity. This is probably the most famous community detection formulation, and kind of sometimes it's kind of in the right direction of a statistical minded approach, but I think it's kind of not how I would have formulated it, but this is kind of the most popular formalism here. In fact, I have a paper where I propose some alternative, but it hasn't caught on as much as this. So I want to talk about the modularity of a group C of subset of V. Okay, and this is often called Q. Q is the letter we assign uppercase Q to a kind of a group, and it's roughly going to be the fraction of the edges in the group minus the expected kind of fraction of edges. Okay, so I want to say the actual number of edges that are in this community versus the expected fraction of edges in the in the community. Okay, and so how I would actually formulate this would be as QC. Often I write it as some bookkeeping why I have this in front here. So I look at all the vertices I and j in the set C, and I look at what's aij minus eij. Okay, well, what is this here? This is the adjacency matrix. right? So this is going to be a 1 if ij is an edge. These are two vertices in the cluster, right? So I have this is C. I have part of a graph that's going to be inside of here. Some nodes are going outside. This would be node I. And this would be node J. Okay, there are two nodes in here, and I want to measure the for all of the nodes inside of here, I and J. If there is an edge, there is an edge in this case. Aij is going to be 1. It's going to be 0 if there's not an edge, right? And then the expected number of edges, okay? The expected number of edges is a little bit more complicated to define. This is going to be defined as di dj divided by 2 times the total number of edges. Okay, why is this? What is dij, where di is the degree of vi, right? So if there's a vertex that has a really high degree, and in fact, both vertices have very high degree, do Mr. Beast and so Taylor Swift, are they friends with each other on so Twitter or kind of on, I would think probably not. I don't know. That'd be be interesting. But so very high degree nodes in a network are more likely kind of, if you just assign a vertex a lot of degree and say, I'm going to assign it which it's connected to at random, well, then I'd say the probability that two nodes are connected to each other is going to be proportional to the degrees of those nodes. If they're a highly connected node that has lots of edges, then they're more likely to be connected to some other node. And so it's the product of those two degrees of those nodes divided by the number of edges. And then I divide by 2 because the degree counts every edge. I count every edge twice if I sum up all of the degrees. Okay. So this would kind of be the expected number of edges if I did it proportional to the degrees. Because the degree sequence is not uniform about these graphs, I have to pay attention to this. Otherwise, I will just find these regions that the expected number is based on the Erdős-Rényi random graph. Then this value is just P everywhere, right? But I need something that somehow is related to the kind of the preferential attachment model. And this is the simplest possible way. Just look at the degree distribution that I see on the graph that I observe and use that degree distribution to say the probability two edges are actually connected to each other. It's proportional to the product of their degrees of the two edges. Okay, and this gives me an expected number. And so if the true number, the adjacency matrix, this is the true number of edges, true number of edges, right? Minus the expected fraction of edges, and this kind of normalizes it so it's a fraction if I did the math right. Then this is the difference between the expected fraction or the fraction of edges I actually observe and the expected fraction of the edges. Okay, this isn't exactly this log likelihood model we talked about in the anomaly detection section. There is a way to write this as a log likelihood ratio model. In fact, this is the paper I had wrote like 20 years ago, but this is more popular. Okay, this is what people study. Okay, so this kind of gives you a notion of modularity, and you want to find a subset that has large modularity. Okay, a community now equals a subgroup C with large Q of C. Okay, so I can compute the modularity score for any subset of vertices. I would like to find one that has a large score measured in this way. Yeah. Oh.
I was gonna maybe ask if the adjacency matrix could, instead of being like, oh, 1 or 0 or the count, if it would be like the problem, if it could be the probability.
Yeah, so I could plug in this similarity score inside of here instead, right? So if I had a richer notion of what the connectivity was, instead of 0, 1 binary, it was a score between 0 and 1, I could plug that in here. I could probably write down a degree that was the sum of all the similarities coming out of the node, and I bet this would work. I bet you could write down a log likelihood ratio score, that extending the paper I wrote that no one pays attention to from 20 years ago. And this would probably give you something new and maybe more robust. I haven't seen a paper that's done this, but that would make a lot of sense to me too. Yeah. Okay. So this is kind of a kind of a common notion of defining the score of a community that's been very, very well studied. 1,000 papers written on studying this topic, probably. Okay, so how do I find these communities? How do I find communities that have a large modularity score? Yeah, so there aren't really good algorithms here. This turn, I mean, it's not like I can, I write the matrix as a graph. I do some, or write the graph as a matrix. I do some reformulation of it. I compute the eigenvectors, and I kind of break into the left and right side. There isn't a simple way of doing this anymore. I kind of need to search all the choices for C, right? If I know a C, I can compute the score. So I can compute the score pretty quickly. But how do I know how to find the C? How do I find the C that maximizes this? Yeah. Could start with the random C. Yeah, probably I'm going to be all over the place, right? There might not even be connected. Probably want a subset that's going to be connected. Yeah, so there's kind of studies of like trying to find the best C, trying to start with a good guess of one vertex and then expand it into kind of larger kind of sets that are well connected. Or you can start with spectral clustering on the graph to give you some cuts into fairly well connected regions. And then you can try and optimize those by throwing out some vertices or adding some vertices in. And these kind of work, but I think this is actually another hard problem to solve. This was kind of invented by people who are not computer scientists, right? When computer scientists invent a method, they invent the method that they think models it well, that they can actually compute efficiently. People from the communities from physics, I think this was invented from the physics community, or in statistics, they aren't burdened by having to compute stuff necessarily. Or they say, oh, I'll run an algorithm and check everything, and it will run for a week on the supercomputer, and that's fine, right? Whereas we want something that's easy, kind of easy to compute. So these things were invented by people who weren't thinking about the computation during the modeling step. Okay, but they are popular nonetheless. Okay. Yeah.
So
I don't know if they're probably trying to do some, I don't know what the best algorithms are. When I played with this once like 20 years ago, and the way we ran this is we started with spectral clustering to kind of try and give some good guesses of what some type clusters in the graph would be. And then we would look at vertices that were in the subset or just outside of it, that were connected to nodes inside. And we would look at all those neighboring vertices and see what happened if we removed them or added them into the cluster, into the group, how that would change the Q-score, computed that for all of them, and all the ones that increased the score by changing them, I would update that. And then I would do this again. This isn't guaranteed to do anything, but it kind of worked okay. We found some high modularity or high kind of hour score kind of parts of the graph, but we had no guarantee that these were the best answers. I think people have studied this where they say the best answer has to be similar to some tightly connected region that you can find through another method like spectral clustering. And then it has to be similar to that. So then I do random walks from that, right? Where I randomly change it in various ways. And it's a random walk on the space of the groups. And I say the random walk will eventually find kind of the optimal thing or something close to it. And maybe you can prove something, but I don't know. It's kind of a mess. I'd rather just use spectral clustering and say, okay, I found groups that way and be done with it. The difference between the modularity groups and those, I don't know how big of a difference it is. But this is well studied in finding communities in graphs. This is kind of the default way to do it. Okay, we have 5 minutes left. Let me tell you about one other kind of obvious way to find groups in small poor communities. These would be just the clicks in the graph. These are fully fully connected C's, which are subsets of V. That means for all ij in C in C, Eij equals 1, right? So this would be an example if I have I have all possible edges for these 5 nodes in this graph. And I can have other edges in the graph. But this would be the click, right? This is the click of size 5. It has all the edges in here. This is a very tight community. If I can find a large click in the graph, this would be a very tight community. People have also studied how to find these large clicks. It's finding the largest click in a graph, or is there a click above some size k, is a classic kind of classic NP-hard problem. But in practice, it's actually not so hard. What you do is you start with all the edges, and then for every edge, you check. Okay, so I'm going to look at an edge here. Okay, then for all the edges, I look at all of the possible edges from this vertex and all the possible edges from this vertex, and I want to see, is this edge part of this is a click of size 2 edges, right? If I want to see if it forms a triangle, which would be a click of size 3, well, I can look at all of the edges coming out of the 2 endpoints, and I only have to check if any of those vertices, these sets. So if I have an edge, and if I have some edges coming out of here, if these intersect, I can only have a triangle if these intersect. So I only need to check these given all the edges. So I compute all the edges, I build the neighborhoods of each of the endpoints, and if those intersect, like this, then I have a triangle. Okay? This step is the slowest part. Now I have a set of triangles. The number of triangles is often way less than the number of edges, typically. Okay? Maybe it's about the same as the number of edges. Okay, but I have to, once I find all the triangles, I want to say, are there any 4 clicks? Well, I don't have to just start from scratch again. I know a 4 click must include a triangle. So for all the triangles now, I look at all of the endpoints, and I look at all their neighborhoods, and I see if there's a common intersection among the neighborhoods of these guys, right? And if there is a common intersection, that means I have a 4-click then. And the number of these is often much smaller now. Okay, now I have the number of 4 clicks, and I only had to look locally here. Then from the 4 clicks, I can look from there to see if there are any 5 clicks. And there's smaller, usually smaller and smaller number in practice. And so this finds the clicks here fairly well, because I can do a lot of pruning. Every K click must have a K-1, a bunch of K-1 clicks inside of it. And so this isn't so bad to do. So maybe I can start by finding all these large clicks and then kind of maybe grow communities from there that are almost clicks. And this is kind of another way of approaching it, which I think is fairly reasonable, but it has a very high threshold. I must have basically almost completely dense for this sort of algorithms to work. Otherwise, I can't do the pruning that I had described here. All right, okay, so hopefully you and kind of this is overview of communities and graphs. We enjoyed the lecture part. I'll see you back here of the class. I'll see you back here on Wednesday for the end term exam. You get up 1.5 pages front and back, so that's 3 sides for the end term exam. It'll be in class. And then don't forget your posters, and I will see you at the poster session on December 12th as well.